Power rule and more. Alright, we've reached it. The easy way to take the derivative of a power function. So previously, we needed to use the limit of a difference quotient definition to find the derivative of a power function, or really any function. But now we can apply the rule that tells us that the derivative with respect to x of a function of the form x to the n, so a power function, equals n times x to the n minus 1. So here's what's happening here, is that we need a variable base. So x is the variable here. So remember this notation. The derivative with respect to x is the variable, raised to a number power. So a real number power is going to equal taking that exponent and bringing it to the front and multiplying it. So n times the variable x raised to that original exponent minus 1. So I move it to the front and then I subtract 1 from the original exponent. So that's going to be the rule we use to take the derivative of power function. So again, what do I need to use the power rule? The base must be a variable and the exponent must be a real number. So that variable has to match the variable we're taking the derivative with respect to. So now we're going to do some examples of applying the power rule to find derivatives. Alright, so in our first example, we've been given f of x equals x cubed, and we were asked to find f prime of x and then find f prime of 2. So let's just rewrite the problem. F of x equals x cubed. So this is a power function. It has the variable x raised to a real number power 3. So our rule tells us that we can find the general derivative as a function, f prime of x, by taking the exponent, so by taking 3 and moving it to the front and multiplying it. So 3 times x, and then what we do is we subtract 1 from the original exponent. So 3 minus 1. So our derivative function is now 3x squared. So 3 minus 1 is 2. So our derivative function is 3x squared. So that is f prime of x. And now what that allows us to do is find the derivative of the original function at any point. So particularly at the point 2. So now what I can do is find f prime of 2. So that's 3 times 2 squared. So 3 times 4 is 12. So graphically, just to sort of sketch what we did, is we had the function x cubed. So you should all know that it looks like this little curve here. And we wanted to find the derivative particularly at 2. So at 2, I would want to draw a tangent line that's in a different color. It's going to have a pretty steep slope, and it's going to be a positive slope. And if I wanted to find that particular value without using the limit of a difference quotient, so here are my options. I could have set up the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h, and solving that limit and using the function would have got us out a value of 12. Or I could have used the limit as h goes to 0 of f of x plus h minus f of x all over h, and what I would have got out is I would have got out 3x squared. I would have got out f prime of x, the derivative function. And then I could have taken 2 and substituted it into 3x squared, but now I have the power rule. So the power rule says as long as the base is a variable and the exponent is some number, I can take the exponent, move it to the front and multiply it, and then reduce the exponent by 1 to get my derivative function. So let's try it one more time now. Here I have f of x equals x to the e. Find f prime of x and then find f prime of 1. So f of x is x to the e. Let's go ahead and just rewrite that. Whoops. That looks weird. So I have x to the e. Alright, so I do have a variable base to a number exponent. So e is a number. It's about 2.718. So what I can do then to find f prime of x is bring the number, the exponent, to the front. So I'd have ex to the e minus 1. Alright, as crazy as it looks, this is how you're going to leave your answer for f prime of x. So what we would not want to do is approximate e. So just like if this was pi, we wouldn't just want to stick 3.14 in, because that's not exact. So we would in fact leave our answer for f prime of x just like this, but we're not done with the problem because we want to find f prime of 1. So f prime of 1, I would replace the x value with a 1. So e times 1 to the e minus 1. This I would simplify, and here's why. 1 to the anything is always just 1. So 1 raised to any power is always going to give me 1. So this quantity right here, 1 to the e minus 1, this is just 1. So 1 times e is just e. So I'd want to leave my answer as e for the second part of the problem, f prime of 1. But there's no simplifying to do on f prime of x, so I would not replace e with the approximation of 2.71 or even carrying it out to more decimal places, because this is an irrational number that has a decimal representation that goes on forever. So I would just leave my answer in terms of e's here, but I would want to apply the fact that 1 to any number is always just 1. I do want to give a warning. The power rule does not directly apply to an expression like the quantity 2x plus 1 to the fifth power. So even though there is an x in here that's being raised to a number power, it doesn't apply to this type of expression. So you'll see in a little bit that you would actually have to distribute this. So 2x plus 1 times 2x plus 1 times 2x plus 1 5 times. So the power rule does not apply to an expression like this. It has to be one variable raised to one number exponent. Alright, so here's another rule that you're going to like, the derivative of the exponential function. So the derivative with respect to x of the exponential function e to the x is e to the x. So this is very specific. It tells us that when I have just the number e raised to the x variable, so the exponential function, the derivative of the exponential function is the exponential function. Alright, and the last thing we're going to take a look at in this section is the linearity rules. So the sum rule says that if we have the function f plus g, and that is differentiable, then f plus g prime equals f prime plus g prime. So in other words, this is sort of an extension of the sum rule for limit laws, because if you remember, a derivative is a limit. So if the function f plus g is differentiable, well then the limits exist, so we can split up the derivative of the sum of two functions to be the sum of two separate derivatives. And then the constant rule, for any constant c, if c times f is differentiable, and we have cf as a quantity prime, that equals c times just f prime. So I can pull the constant out and sort of leave a constant off to the side while I do the derivative of the rest of the function. So now what we're going to do is apply the linearity rules and then what we know now about the power rule and the derivative of e to the x to solve a couple of problems. So given f of x equals x squared plus 1, find f prime of x. So f prime of x here. So what this sum rule allows us to do, and it also carries over to subtraction, tells us that what we can do is take the derivative of each piece of the function separately if they're being added or subtracted. So in other words, first we're going to do the derivative of x squared. So by the power rule, I have a variable raised to a number exponent. I can take the 2 in the exponent and move it to the front. So it would become 2x, and then I'd have to subtract 1. So 2 minus 1 is 1. So it would just be 2x, because we really wouldn't write a 1 on the exponent. And then plus, this is its own function here. This is the function 1. So this is going to represent a horizontal line. So in other words, I'm taking the derivative of each piece separately. If I ask you to find the derivative of just y equals 1, or the horizontal line, the slope of that line is 0, so it's 2x plus 0. So f prime of x here is just 2x. So now let's look at the second example, we're going to find the derivative of 2x cubed plus e to the x. So the derivative f prime of x, I'm going to take each piece separately. So first the derivative of 2x cubed. So bring the power to the front. Now, what about this 2? The constant law says I can pretty much just ignore the 2 and bring it to the front. So let's just leave the 2 there. And then now we're going to think about taking the derivative of just x cubed. So I can apply the power rule. I have x to the third power, a variable to a number exponent. Bring the 3 to the front, so 3x, and then subtract 1 from the exponent, so 3 minus 1 is 2. And then plus, now I'm taking the derivative of e to the x, which is the nice e to the x. So here I have 6x squared plus e to the x. And that's going to be my f prime of x. Now we'll go ahead and move on to some more examples using some different notation that still tells us to evaluate the derivative. So d dx means find the derivative of the function the square root of x. Now we can apply the power rule if we rewrite the square root as x to the 1/2. So I am taking the derivative with respect to the variable x of the function x to the 1/2. So I can only apply the power rule if the variable here, so this is with respect to x, is the base, and then I have a number in the exponent. So now I've rewritten this square root function to have a fractional exponent instead of thinking of it as a square root so that I can apply the power rule. So I'm going to bring the exponent to the front. So now I'm actually evaluating the derivative, so I can drop the derivative symbol in front. This was telling me to take the derivative. Now that I'm actually doing it, I'm not going to include it in this next step. So I bring the 1/2 to the front, leave the exponent the same, and then I'm going to subtract 1 from 1/2. So it's going to be 1/2 minus 1. So I'm going to go ahead and simplify now. This is 1/2 x to the negative 1/2. So if I subtract 1, that's like 2/2. And then I'm adding the opposite. So I get an exponent of negative 1/2. So now I can go ahead and simplify this just a little bit further. Often this would be a multiple choice question, and I wouldn't want to leave a negative exponent. So this is 1/2. And if this is x to the negative 1/2, the term with the negative exponent would move to the bottom of the fraction bar. So this would be x to the positive 1/2. And then also, we often don't like seeing fractional exponents, so you'd probably see the final answer written as 1/2 times the square root of x. So this is the most simplified answer. Now, we could rationalize and get rid of the square root on the bottom, but this is fine. We're just going to go ahead and stop right here. This is the derivative of my original square root function. So now let's take a look at another example. I have the derivative with respect to the variable x of x to the negative 3. Now again, the variables here match, so the base is a variable, the exponent is a number, and it can be any real number as the exponent, and we can apply the power rule. So even though this is negative, that's perfectly okay. We're going to jump straight to finding the derivative. So I'm not going to put that d dx in front because that would tell me to take the derivative, and that's what I am already doing by the next step. So I'm going to bring the negative 3 to the front, so negative 3 x, and then I'm going to have to subtract 1 from the exponent, so negative 3 minus 1. So now I'm going to simplify this. This is negative 3x, and then negative 3 minus 1 is negative 4, is my new exponent. And again, to avoid negative exponents, I'm going to go ahead and bring the term with the negative exponent to the denominator. So this is a common mistake people make, is they bring the negative 3 to the denominator, but the term with the negative exponent is just the x. Only x is being raised to the negative 4. So this would be negative 3 in the numerator, and then x to the negative 4, if brought to the bottom of the fraction bar, becomes x to the positive 4. So there's really a multiplication happening here. Negative 3 times x is the only thing raised to the negative 4. So that's the only part that goes to the bottom of the fraction bar. So this here is going to be my final answer. And then taking a look at the last one, I have the derivative with respect to x of the cube root of x squared. So here's another example, just like the first one, where I'm going to have to rewrite this so that it's x as the base, because it's the derivative with respect to x, and I need a number in the exponent. So I'm going to need the ddx part. I haven't taken the derivative yet. I'm just going to simplify this portion. So what was underneath the cube root is x squared. So x squared is being taken to the 1 over 3. So a cube root turns into the fractional exponent 1 over 3, which now I can multiply by properties of exponents. So this becomes the derivative with respect to x. Because I have not yet taken a derivative, I'm only going to simplify the exponent. So multiplying 2 times 1/3, I get 2/3. So now that I have a variable in my base that matches the variable with the ddx portion, I can apply the power rule because I have a number in the exponent. So the number in the exponent is going to move to the front, 2/3 x, and then I'm going to need to subtract 1 from 2/3. So simplifying it a little bit more, we're going to get 2/3 x. And if I subtract 1, well, subtracting 1, I'm going to need my common denominators. It's like subtracting 3 over 3. So I'm going to get negative 1/3 as my new exponent. So now again, I don't want to have any negative exponents, so I'm going to rewrite this as 2 over 3 x to the 1/3. And if I wanted to avoid having fractional exponents, I could rewrite this as 2 over 3 and then times the cube root of x. And again, we could do some rationalizing, get rid of any radicals in the denominator, but we'll just go ahead and leave our answer like this. We've done a lot of simplifying already. The main thing we want to avoid is any negative exponents for the most part. And then again, noticing that the only portion that went to the denominator was the x to the negative 1/3. The 2 stayed in the numerator, and the 3, of course, is in the denominator, and that's why the 3 is being multiplied by x to the 1/3. That's the only portion that moved to the bottom of the fraction bar. Alright, now we're going to try some different examples. We're going to mix it up a little bit and include different variables. So now we're going to try to take the derivative with respect to the variable k of the expression k squared minus 3. So by my linearity rules, I can take the derivative of each piece separately, and the first one can be solved using the power rule. So I'm going to take the derivative with respect to k of k squared. So the derivative of the first part, well, I'm just going to go ahead and bring that 2 to the front. So it's going to be 2k. And now I have a 2 in the exponent that I'm going to have to subtract 1 from. So in fact, I'm just going to get 2k to the first power, and we really don't ever write the first power. So the derivative of the first part is k squared. And now, since these two terms, again, are being added or subtracted, I can take the derivative of the second piece separately. So I did the derivative of k squared, I brought the 2 to the front, and then reduced the exponent by 1, which made it a 1. So 2k is the derivative of the first part. And now taking a look at the derivative of negative 3, or the derivative of just 3. So I'm subtracting the derivative of 3. Well, the derivative of any constant is 0. The derivative of 3 is 0. So remember that derivative is the slope of a tangent line. If I'm just focusing on 3, 3 is a horizontal line. So the derivative of 3 is just 0. So my final answer would just be 2k as the derivative of k squared minus 3. And moving on, we're going to go ahead and take the derivative with respect to the variable y now of pi times y minus y cubed. So again, I have two terms that are either added or subtracted, so I can think about doing each derivative separately. So the derivative with respect to y of pi y, well, I can apply the power rule here, so there is really just a 1 in the exponent. So if I bring that 1 to the front, I'm going to get 1 times the pi that was already there, and then y to the 0. So if I subtract 1 over here, so here was a 1 already, if I bring the 1 to the front and subtract 1, I'm going to get y to the 0. So let's go ahead and leave that there for a second, and then let's keep going. So now we're going to have minus. Again, I can do each derivative separately. So now the derivative of y cubed, well, I have my variable y as the base, 3 as the exponent. So I bring the exponent to the front. I'm going to have 3y, and then I'm going to subtract 1 from my exponent. So if I subtract 1 from 3, I'm going to get out 2. So 3y squared is the derivative of y to the third power. So I did each one separately, and now I want to simplify. So I have 1 times pi, and that's just going to give me pi, and y to the 0, well, anything to the 0 is just 1. So this left side right here is just pi, and then minus 3y squared. So I'm going to go ahead and leave that as my final answer. I was able to take the derivative of each piece separately, and the derivative of the first part was just pi. The derivative of the second part was 3y squared, and because they were subtracted, my final answers are also going to be subtracted. The linearity rule says I can take the derivative of each piece separately as long as everything is being added or subtracted, or each term is being added or subtracted. Now, real quick, I want to focus on, well, why is the derivative of pi y just pi, without kind of showing this work right here. So let's sort of think about what's the derivative of, how about 3x minus 2? Well, what we learned before was that the derivative of any linear function, so this is a linear function right here, was just the slope of the line. Well, the slope of the line here is just 3. So the derivative of this would just strictly be 3, because the derivative of a linear function, this is of the form mx plus b, we know it's a line, is the slope of the line. Well, on this problem, I'm taking the derivative of each piece separately. So pi y I'm considering is separate from y cubed. And just pi y, that's a linear function. So we can kind of think of it as mx plus b, but there is no y-intercept. So the derivative of this portion here is the slope of the line. Well, the slope is pi. It's not a whole number or an integer, but it is still the slope of the line. It's the m value. So that's why it turned out that this ended up just being pi. But again, we could have used the power rule because this was raised to the first power. This y variable's exponent was a 1. Alright, and now moving on to the last example here. I have the derivative with respect to the variable z of 2 over z squared. So right now, with the way that this is written, I cannot apply the power rule. Again, I cannot apply the power rule. The power rule says that I need the variable z raised to an exponent. Right now, I have 2 over the variable z raised to an exponent. So I'm going to have to do a little bit of rewriting before I can apply the power rule. So I have not yet applied the power rule. I need this ddz portion. And what I need to do is I need to rewrite this so that it is, in fact, a variable written to a number exponent. And I can have a number in the front. So the 2 that's in the numerator, well, that's going to stay in the front, because what I'm going to do is move z squared to the numerator, which will make the exponent the opposite sign. So it was a positive 2 in the denominator. I'm going to have to move it to the top and make it a negative 2. Now I can apply the power rule. I cannot apply the power rule to just the numerator and denominator. We have a whole separate rule when I have rational functions or a function that looks like a fraction later on that I have to apply. This is something where I'd have to rewrite it so that it is all on one line. So I have 2z to the negative 2. So I have this z base with a numerical exponent. So now I can apply the power rule, which says I will take the negative 2 and bring it to the front. So there's already a 2 there. So I'm going to put the negative 2 in front. And then I'm going to have z. And what I'm going to need to do is subtract 1 from negative 2. So negative 2 minus 1. And as we do more of these, you'll be able to do all the subtraction in your head and not show this work. But I want to make sure and show every step. So negative 2 times 2 is negative 4. and then I have z to the negative 3. So if I add the opposite, my new exponent is negative 3. And if I want to avoid negative exponents, I'm going to rewrite this as negative 4 over z cubed. So again, only z is being raised to the negative 3, so that's the only part that moves to the denominator. So this is my derivative. Now before I move on, one of the things I want you to observe is that if at the very beginning we thought we could just apply the power rule to this denominator portion, because you see this z squared and you think, okay, I can apply the power rule, let me just bring the 2 to the front and then leave the z and then reduce the power by 1, so I'm going to get 2z to the 1 on the bottom. And then I have my 2 on the top, and a lot of people just say the final answer is 2 over 2z. Or they maybe cancel out the 2's and say the answer is 1 over z. Well, hopefully you can see how just not true that is. So the final answer was negative 4 over z cubed, which is definitely not the same as 1 over z. So my point is, you cannot just apply the power rule to the numerator and the denominator separately. The only way to apply the power rule is if I have my function all on one line, and if all of the terms are being added and subtracted. That's when I can do each piece separately, not a numerator and denominator. That does not work. All right, now let's move on to a couple more challenging examples. If I have given this function, x minus 3 is one quantity, multiplied by 3x plus 2 is another quantity, I'm asked to find f prime of x. So now we're just looking at different ways we can be asked to find the derivative. So given this original function, find f prime of x, find the derivative with respect to the variable x. Now the way that this is currently set up, I cannot directly apply the power rule yet. So again, I can only apply the power rule when everything's on one line, so I do have that happening, but all my terms need to be added or subtracted, and right now I have these two expressions that are multiplied. So the first thing I need to do is distribute. So I'm going to have x times 3x, so that's 3x squared, and then outer, so I'm going to have plus 2x, and then minus 3 times 3x is minus 9x, and then finally I'm going to have minus 6 will be distributed, so I get 3x squared minus 7x, combining these like terms, minus 6. So this is the function f of x that I want to work with in order to find the derivative, because now all of these terms are being added or subtracted. Well, they're all being subtracted, but it's fine, added or subtracted from each other, and they are all of the form where I can apply the power rule. I have the variable x as the base and numbers as my exponents. So I have 3x squared and then minus 7x to the 1, and then I have this constant term, I have this 6. So when I attempt to find the derivative right now, I can find the derivative of each piece separately. So first let's find the derivative of 3x squared. So I can go ahead and bring the 2 to the front. So 2 times the 3 that was already there, and then x to the first power, because remember I'm going to subtract 1 from the 2. So I have x to the first power, and then minus, well now I'm going to take the derivative of the second piece. Now let's try to remember something, that 7x, this is a linear function. So the derivative is just the slope. So the derivative of this piece is just 7. Now again, I can apply the power rule if I want, so let's show that step. That's 1 times 7 x to the 0. So remember, I'm going to subtract 1 from this exponent, which is going to give me an x to the 0. So 1 times 7 is 7. Anything to the 0 is 1. And so this piece right here is just 7. And if I take the derivative of a constant, just a number, well, that's a linear function too, just by itself. 6 is a horizontal line, and the slope of a horizontal line is 0. So now if I go ahead and simplify this, well, I have 2 times 3, that's 6x, and we never write to the first power, we're just going to leave it as 6x, and then minus 7. So the derivative is 6x minus 7. So again, I can't just apply the power rule to this piece, and then apply the power rule to this piece, and then multiply those two pieces together. That will not work. We have a special rule when I have terms that are being multiplied or expressions that are being multiplied. So in this case, I would apply the power rule by first distributing and getting a bunch of terms to be added or subtracted. And now let's look at this example. I have x cubed minus 3x squared divided by x. Now again, I want to clarify, I cannot just take the derivative of the top using the power rule and then the derivative of the bottom using the power rule. That is not a rule. That will give you the wrong derivative. What I have to do in this case, what I can do, is I can simplify. Because I have 1x on the bottom, and I have a property of fractions that tells me that I can rewrite y to be x cubed over x minus 3x squared over x. So I can take this term over x and subtract it from this term over x. And then I can do a little bit of reducing. So x cubed over x becomes x squared. So this was an x to the 1, and I'm subtracting the smaller exponent from the bigger exponent. And then here, this is an x to the 1, so this is going to become minus 3x. So if I subtract 1 from 2, I'm going to get x to the first power. So in other words, this expression is really the same as x squared minus 3x, which is perfect for using the power rule. I have two terms now that are added or subtracted. Originally, I did have two terms added or subtracted, but I also had division involved. I was dividing by x, so I would need to stop right there and say, as it is, I cannot apply the power rule. So now, what I can do is apply the power rule to the simplified version. I can go ahead and bring the 2 to the front of the x. So now y prime equals 2x to the first power. And we never write to the first power, so just 2x. And then minus 3. So as you can see, I'm writing a little bit less and less every time because the power rule should be something we're so good at, we don't really need to show too much work. So we would want to show the work for the simplifying part, but for the derivative, let's sort of think about it. The derivative of x squared, well, I brought the 2 to the front, and then I subtracted 1 from the 2. So that would just be 2x to the 1. And then how did I get 3 as the derivative of the 3x portion? So remember, 3x is a linear function, right? X to the 1 is linear. And the derivative of a linear function is the slope of the line. So the slope being 3. So my derivative, or y prime, is 2x minus 3. So again, just alternate notation. Given y, find y prime. Up here we were given f, find f prime. Previously, we were asked to find ddx or ddk or ddy, find the derivative with respect to a particular variable. So all of these are different ways to be asked to find the derivative. So now two more problems. In this one, we're asked to differentiate. Again, yet another way we're asked to find the derivative of x minus 2x squared over the square root of x. So I want to apply that same type of reasoning from last time where I split up this function before I attempt to find its derivative. So I'm going to have to rewrite this as x over the square root of x minus 2x squared over the square root of x. And then I'm going to need to do some simplifying. So this is an x to the 1. So this is x to the 1 over x to the 1/2. And then minus 2x squared over x to the 1/2. Now this is a review of exponents, which is really important because this has come up so many times and a lot of students get it incorrect because of their properties of exponents being confused. So what's happening here is I'm technically bringing this x to the 1/2 to the numerator. And when I bring it to the numerator, it's going to have to become x to the negative 1/2. And these two are being multiplied, the x to the 1 and x to the negative 1/2. And when I have the same base, we add the exponents. So this is x to the positive 1/2. If I add 1 to negative 1/2, I get positive 1/2. Or, you don't actually have to show this intermediate step that I've shown from here to here. What's really happening is that I'm subtracting 1/2 from 1. So I take the smaller exponent and I subtract it from the bigger exponent. So it moves to that side of the fraction bar and I subtract the smaller one from the bigger one. And a lot of people understand it when it's whole numbers. So just to pull an example off to the side, if I have x cubed over x to the 1, well, everyone seems to understand that this is x squared for a few reasons. Well, if I have x cubed, that's really 3 copies of x being multiplied to each other, and then I have this x on the bottom. So that means one of the x's cancels out because this is all multiplication and division. So what I have left is just 2 copies of x, which is x squared. But the other thing that's happening is I have x cubed on the top, and x to the 1 moves to the numerator through multiplication and becomes x to the negative 1, and then I'm adding those exponents. So x to the 3 plus negative 1 is x squared. So a lot of people seem to understand it when it comes to whole numbers, but when it becomes fractions, it gets all mixed up. And we are going to deal with a lot of fractions here. So let me go ahead and erase all this. That was just to sort of help you understand the whys. All right, and so now we're going to go ahead and keep going and try to do the same thing on this right-hand side. Whoops, I lost a term. 2x squared. All right, so now on the right-hand side, I'm going to have my minus 2. So the 2 is in the numerator. It's just going to stay on the same line because it's like a 2 over 1. And then let's write what's actually happening. I have an x squared, and the x to the 1/2, just like over here, moves to the top, becomes multiplied by x to the negative 1/2. And now if I add these together, if I add these exponents, 2 plus negative 1/2, well, that's 1/2, but we don't use mixed fractions in this class, so it's 3/2. So minus 2x to the 3/2 is what this becomes. Now, I want you to take a second to realize that we have not done any calculus yet. We've merely done simplifying. So we have rewritten this expression so that it is 2 different terms being added or subtracted so I can apply the power rule. So now I'm actually going to differentiate. I'm going to find the derivative with respect to x of x to the 1/2 minus 2x to the 3/2. So if I attempt to find the derivative of this, well, now I can use the power rule. I can bring the 1/2 to the front, so this equals 1/2 x, and remember, I would be subtracting 1. Now, if I subtract 1 from 1/2, I get negative 1/2. And now I'm going to bring this 3/2 to the front, so I'm done with the derivative of the first term using the power rule. Now the derivative of the second term using the power rule. So I'm going to bring the 3/2 to the front, and there was still that 2 there. And then x to the, well, if I subtract 1 from 3/2, I'm going to get 1/2. So if I subtract 2 over 2 from 3 over 2, I'm going to get 1 over 2. And now let's do our simplifying. So this left side, the negative 1 over 2 exponent, is going to move the term, just the x term, to the denominator. So this is 1 over 2x to the 1/2 minus this 2 over 2 is going to cancel. So I have 3x to the 1 over 2. So I can continue to do a little bit more simplifying. And in the future, we're going to need to simplify this a little bit more by forcing common denominators, and that's just going to make things a little more complicated for now, which is a little too early to get into that. So let's just stop right here. This is the derivative of my original function. So I don't have any negative exponents. I do have fractional exponents, so we could rewrite these as square root of x's, but we're just going to go ahead and stop here and leave it here for now. So just to clarify, I could not take the derivative of the top and bottom separately because there's a separate rule for that entirely. So if I wanted to use the power rule, I need to split this up because there is 1 term on the bottom and 2 on the top being added or subtracted. So that's why I can split things up. And then I really do need to understand my properties of exponents. So one of the things I do just want to clarify, because this is the most common mistake, is what a lot of students do, and I have no idea where it comes from, is they write this. So they have that top piece, x minus 2x squared, and then for whatever reason, they bring this to the front. So they recognize, well, this bottom is x to the 1/2, and they bring it to the top through addition somehow. So they bring this up and make it x to the negative 1/2, and they add it. So not true. So I have no idea where this is coming from, but I have a good 5 or 10 students every year that just keep doing this over and over and over again. So this is not true. This does not work. So the best strategy is to just split it up right away. There is a way to move this to the top, but it's through multiplication, and then I'd have to distribute, and it's just a little bit trickier than what I've shown here. So split it up first. Do not attempt to move the square root of x or the x to the 1/2 to the top. It definitely doesn't go to the top through addition by any means. But in general, it's not the way I would recommend doing this. All right, the last problem. So this problem is slightly different, the notation is, and it's asking us to do something slightly different. So this problem is saying, find the derivative of the function y with respect to x at the x value 1. So I would expect you to be able to read this statement. So find the derivative of the function y with respect to the variable x at the x value 1. Given the function y equals x squared times the quantity x minus pi. So here's what the problem is asking us to do. It's asking us in order to first find the derivative of the function y with respect to x. Then once we've done that, then we plug in the value 1. We never plug in the value 1 first. Yes, it would make our lives a lot easier, but it would also make the answer completely wrong. And it would in fact make the answer 0 every single time. Because if I just plug 1 into this function, into the x's, I'm going to end up with a number value. If I take the derivative of a number, the answer is always 0. So again, I do not ever plug in the x value first. So that's what this note on the bottom says. We always find the derivative of the function before substituting in the numerical value if 1 is given. So this is the first example we're doing and the only example we're going to do of plugging in a numerical value. But it's just a small extra step at the end. It works the same way as far as finding the derivative like we have for the previous examples. And then the last step is just to plug this x value into the derivative once we're done. So now let's take a look at the function. The function is x squared times the quantity x minus pi. Now the way it is currently written, I cannot directly apply the power rule. I can only apply the power rule when terms are being added or subtracted. I have this term multiplied by this expression. So because I have this multiplication here, I have to do some simplifying first. In fact, I have to distribute. So let's simplify y first. I have x squared times x, so this is the distribution happening. So x squared times x to the 1, we add their exponents, so x cubed. And then I'm going to distribute x squared times pi, so minus pi x squared. So now these terms are being added or subtracted, so I can apply the power rule to each one separately. So y prime, the derivative of this function y, which is dy dx, so I'm using derivative notation interchangeably. So y prime, the derivative of y, is going to be, well, if I bring the power to the front, I'm going to have 3x. If I subtract 1 from the 3, I'm going to have 3x squared. So now I've taken the derivative of this first portion. Now let's take the derivative of this portion. So I have x as the base, so I bring the 2 to the front. So there was subtraction between the two. So 2 to the front times pi, and then x raised to the first power. So this 2 here is being brought to the front, and then I'm going to subtract 1 from it. So if I subtract 1 from 2, I get out 1. And in the front, I'm just going to leave 2 times pi exactly. So I wouldn't want to substitute in an approximation for pi. I'm just going to leave my answer like this. So I'm not done yet. In the previous examples, I would have been done. Just find y prime, or just find dy dx. But I'm asked to find the derivative of y with respect to x and then plug in 1. So another way to write that, because I've rewritten dy dx as y prime, is to find y prime of 1. Or plug in a 1 for every x that's in the derivative we just found. So 3 times 1 squared minus 2 pi times 1. So in other words, 3 minus 2 pi is my answer for the derivative of y with respect to x at the x value 1. So the answer is 3 minus 2 pi. And I want you to recognize the difference. 3 minus 2 pi, this is a number. What does this number represent? This number is the slope of the tangent line to the function y, to y, at the specific value x equals 1. So when we found y prime, this is the slope of the tangent line at a generic x value. So this too is the slope of the tangent line, but it's at x. So this is a function. What we found right here, this was the derivative as a function. This second part, after plugging in 1, we got out a number. So this is the particular slope at the x value 1. So whatever the curve looks like, I don't know what x squared times x minus pi looks like, or this function here, I don't know exactly what it looks like. I'm just going to make something up. But at the value 1, what we just found was that the slope of the line is 3 minus 2 pi. So that's what we just found, a particular slope. And in fact, this graph is wrong that I just drew because 3 minus 2 pi is a negative value. And right now what I just drew was a positive slope. So this isn't true. We know from this piece of information that at 1, I have a negative slope, right? Because 2 times pi is like 6 point something, so 3 minus 6 point something, I'm going to have a negative slope at the x value 1. So maybe the graph looks something like this. So right at 1, I have this negative slope for the tangent line. So again, when I have a numerical value, first take the derivative, and the last thing you do is plug in the number.